You've sent us this research paper about a new approach to AI,
Okay.
specifically how language models can access and use external information. It's called RetroLM.
Right.
And from what I've skimmed, it sounds like it could be a game changer.
It is an interesting development.
Yeah.
It attempts to address a problem that we're seeing with large language models, or LLMs.
Right. For our listener who might not be familiar with LLMs, could you
Yeah.
quickly explain what they are?
LLMs are essentially complex algorithms that are trained on an enormous amount of text data.
Okay.
This training allows them to do things like write different kinds of creative content, translate languages, or answer your questions in a really informative way.
Right, but they have this tendency to hallucinate, if I'm using that term correctly.
Yes, hallucination is the term we use to describe LLMs confidently generating incorrect information.
Okay.
This occurs because their knowledge is limited to what they were trained on.
So that's where this RetroLLM research comes in, and that's what today's deep dive is all about. We want to understand how this new system can solve this problem of hallucination.
Okay.
Let's first explore the problem in a little more detail.
Yeah.
And then look at how RetroLM works.
Okay.
And finally, we'll examine its performance.
Sounds good.
Yeah.
Hallucination is a real obstacle for LLMs to be reliable.
Yeah.
Imagine you're relying on an AI for important information and it confidently gives you inaccurate data.
Right.
That could have some negative consequences, especially when accuracy is critical.
Totally agree.
Yeah.
So how do researchers try to fix this? I mean, LLMs can access the internet, right?
They can.
Yeah.
But the traditional methods of connecting LLMs to external sources of knowledge, like separate search engines, can be inefficient and use a lot of resources.
Okay, I understand.
Yeah.
What are some problems with these traditional methods?
Sure.
The research paper mentioned something called false pruning.
False pruning is an issue where the model gets distracted by irrelevant information during retrieval and misses the right answer even if it's in the knowledge source. Appendix B in the paper gives a good example of this using a simple question like, what is the capital of France?
What happened in that example?
Imagine the model is searching for evidence to answer the question.
Right.
It starts by focusing on phrases like the capital, but then for some reason it latches onto a phrase like the capital of America and gets stuck.
It gets fixated on this irrelevant path
Yes.
and can't find the right evidence.
Even though that information about Paris exists in the knowledge base.
Wow. So we need a more intelligent way for these LLMs to search for evidence.
We do.
Is that what RetroLM is all about?
It is.
Is it all about better retrieval?
It is, but it's more than just making retrieval better.
Okay.
What makes RetroLM unique is how it integrates retrieval and generation into a single system.
Let's unpack this.
Sure.
How does RetroLM actually work?
Instead of relying on a separate retriever, RetroLM generates evidence from the knowledge source during the generation process. It does this in 3 stages.
Okay.
The first stage is called clue generation.
So it's like the AI is coming up with its own search terms.
Think of it that way.
Okay.
In this stage, the model predicts key phrases or clues that are likely to appear in relevant documents.
Got it.
If the question was about a specific movie, the clue might be the title of that movie.
And then it uses these clues to find the right documents.
The next stage is called document scoring, where RetroLM ranks documents based on how well the generated clues match the content.
Okay.
The higher the match score, the more relevant the document is considered.
Wouldn't that run into the false pruning problem we just talked about?
That's where the third stage comes in.
Okay.
Forward-looking constrained evidence generation.
Right.
This stage is a really innovative aspect of the system. Instead of simply looking for matching words, RetroLM uses something called an FM index to look ahead and predict the relevance of future sequences.
An FM index.
An FM index is a data structure that allows for very efficient searching within large amounts of text.
Okay.
It's used in RetroLM to look beyond the immediate words and anticipates whether the path it's on will actually lead to relevant evidence.
So it's like the AI is saying, this document mentions the clue, but based on what I know about the rest of the document, this is probably not what I'm looking for.
Right.
I need to keep searching.
That's a great analogy.
Okay.
To make this process even more efficient, RetroLM merges these future windows or sections of text that it's looking at. If they overlap, it minimizes the amount of processing needed.
I'm starting to understand how this could be a big improvement over simply grabbing chunks of text.
Right.
Are there any examples of these clues and how they guide the search in the paper?
Yes. Table 9 in the paper gives a good example.
All right.
For example, if the question is, When does the movie The Star come out?
Okay. That's a pretty straightforward question.
Right.
What happens?
The model first generates the clue The Star,
Right.
which, as you can probably guess, is the title of the movie. Then, in the evidence generation stage, it searches for and retrieves text segments that not only mention the star, but also contain information relevant to a release date.
So it doesn't get stuck on a section about a different movie that also happens to be called The Star, because the surrounding text doesn't support that interpretation.
And this whole process of generating evidence is happening within the generation process itself.
Okay.
This is a big change from how traditional RAG systems work.
RAG.
RAG stands for Retrieval-augmented generation,
Okay.
which means the AI uses external information to help generate answers.
Got it. This all sounds pretty impressive.
It is.
But does RetroLLM actually perform better than the older methods?
To answer that, we need to look at the results of their experiments.
Let's do that. I'm curious to know if this cleverness translates into better answers. This is where it gets interesting.
They tested RetroLLM on several different datasets,
Okay.
including ones for both single-hop and multi-hop question-answering tasks. This means they tested how well it could answer questions that require either looking up a single piece of information or combining information from multiple sources.
So like the difference between a simple fact lookup and having to do some detective work to put together a complete answer.
They compared RetroLM to a range of other approaches,
Okay.
including some sophisticated RG systems.
Got it.
Table 1 in the paper summarizes the results of these experiments.
Okay. Before we get to the results,
Sure.
what exactly were they measuring?
Okay.
Just whether or not the AI got the right answer?
They looked at a few different metrics.
Okay.
Accuracy, whether the LLM provided the correct answer was important, but they also considered the F1 score.
Okay.
This measures how well the AI's answer matches the ideal answer,
Okay.
taking into account both precision, which is getting the right information, and recall, which is not missing any important part of the answer.
So it's not just about getting the main idea.
Right.
It's about providing a complete and accurate answer.
Exactly.
Were they measuring anything else?
Yes. They also track the number of tokens consumed by each system.
Okay.
Tokens are basically the building blocks of language for these models.
Okay.
The fewer tokens a system needs to process, the more efficient it is.
So that's like a measure of how much mental effort the AI had to expend to get the answer.
Yeah.
The fewer tokens, the less brain power used.
Efficiency is important, especially as these models and the datasets they're working with become more complex.
Right.
Now, are you ready to hear about how RetroLM actually performed?
Yes, absolutely.
Yeah.
Tell me about the results.
On most of the datasets they tested, RetroLM actually outperformed the other methods, including those more complex RG systems.
Wow.
For example, on the natural questions dataset,
Yeah.
RetroLM achieved an accuracy of 61.6% and an F1 score of 49.8%.
Okay.
That's considerably better than the naive RAG approach, which only got 52.4% accuracy and 41.1% F1.
Okay, so that's a noticeable improvement.
Right.
And what about those tokens?
Yeah.
Was RetroLM any more efficient?
Yes, that was another interesting finding. Okay.
RetroLM used noticeably fewer tokens than traditional RAG methods. It used about 2.1 times fewer tokens than naive RAG on average.
So not only is it getting better answers, but it's also doing it with less effort.
Right.
That's really impressive.
It is.
Does the paper explain why it's so much more efficient?
They suggest that the efficiency gain is likely because RetroLM can retrieve more fine-grained evidence.
Okay.
Because it's not just grabbing whole chunks of text, it can be more selective and focus on the specific information that is relevant to the question.
It's like reading a summary instead of having to read the entire book.
That's a good comparison.
Yeah.
It allows the model to avoid processing unnecessary information, which saves on tokens.
That makes sense. But even though RetroLM is outperforming these other methods, there's always room for improvement, right?
There is.
Did they mention any limitations or areas where it could be better?
They acknowledge that there are still areas for improvement, particularly when it comes to speed.
While it's faster than some of the complex ARG system, it's still a bit slower than the very basic approach, naive RAG.
Okay.
They mention an idea called speculative decoding as a potential way to address this.
Speculative decoding. What is that?
It's a technique that involves using smaller, faster language models for some parts of the process,
Okay.
and then switching to a larger, more powerful model when it's needed.
So it's like having a team of AIs working together, each specializing in a different task.
That's a good way to think about it.
Okay. Would that make a difference in speed?
They think it has potential.
Okay.
By strategically allocating resources, they could potentially speed up the overall process without sacrificing accuracy.
So it's not just about making the AI smarter,
Right.
but it's also about making it work smarter.
They also highlighted another area for improvement.
Okay.
While RetroLM unifies the retrieval and answer generation steps, it doesn't encompass all the other processes that might be involved in answering a question.
What do you mean?
For example, things like analyzing the intent behind the question or figuring out whether external information is even needed.
So the difference between just giving an answer and showing your work,
Right.
explaining how you got there.
They believe that incorporating these additional reasoning processes into RetroLM could make it an even more powerful and comprehensive system.
So even though RetroLLM is a step forward,
It is.
it seems like there's so much more we can learn about how to make these systems truly understand and use information.
It will be interesting to see what future developments come out of this work.
Yeah, I agree.
It'll be interesting to see where this goes.
Yeah, this whole idea of retrieval within generation.
Right.
It's really fascinating.
It is.
It seems like this is getting us closer to AI systems that can access and process information like humans do.
Yeah.
Where they can connect ideas and anticipate what's coming next.
It's a big shift from just viewing AI as like a collection of facts.
Right.
It seems like RetroLM, with this focus on dynamically generating evidence,
Is using a more complex form of information processing.
and it's also a big plus that it's more efficient,
Right.
using fewer tokens.
Yeah.
It means that this approach isn't just a good theory, but it's also practical.
Exactly.
You mentioned some limitations to this research.
Yeah.
They had to rely on a separate system for clue expansion right there.
They used a pre-existing model called Splayed AV3 to expand the initial set of clues.
Okay.
And this was necessary to make the retrieval process more robust.
So it's like having an assistant to double check that no important information is missed.
While RetroLLM's clue generation is effective,
Right.
it's not perfect.
Sure.
So using Splayed AV3 helps to ensure the model considers a wider range of relevant information.
So having to rely on this external system
Right.
isn't ideal.
The researchers acknowledge that relying on Splayed AV3 prevents optimizing the entire RAG task from start to finish.
Okay.
Ideally, they would like the model to handle clue expansion internally.
So it's like a bottleneck.
Yeah. That hinders the system's efficiency and possibly limits its overall performance.
It's important to remember that even with this limitation, RetroLM is still performing better than other methods.
Right.
This is a testament to their approach,
Sure.
but there's clearly room for improvement.
They've built a fantastic car,
Yeah.
but it still needs a little push to get up to speed.
It's exciting to consider the possibilities once this hurdle is overcome.
Yeah.
A truly end-to-end RetroLM system with every component working seamlessly could be even more accurate and efficient.
You mentioned incorporating more reasoning processes into the system.
Right.
Things like analyzing the intent behind a question or figuring out if external information is even needed.
Yeah.
Do you think this is a realistic goal?
I think it's a goal worth pursuing.
Okay.
Right now, RetroLM primarily focuses on retrieving and using relevant information, but it doesn't truly understand the question.
Right.
Adding reasoning capabilities could lead to AI systems that are much more sophisticated and capable of more complex forms of information processing.
So it's like teaching the AI not just to find answers,
Exactly.
but to understand the meaning behind those questions and why those answers are important.
It's about moving beyond retrieving information toward a more complete form of understanding.
Right.
Imagine an AI that can answer your questions, explain its reasoning process, and even offer different interpretations.
That would be incredible.
Would it?
It would be like having a conversation with an intelligent agent
Right.
that can interact with information on a deeper level.
Exactly.
Do they mention specifically how they might incorporate these reasoning processes?
They don't go into specifics in this paper, but it's a direction they see as important for future research.
Okay.
I think it's a natural progression from what they've already done with RetroLM.
Sure.
They've created a good foundation. Now they need to build upon it.
I'm interested in this speculative decoding idea.
Yeah.
Using different AIs for different tasks seems like a clever way to optimize performance.
It does.
But I don't understand how that would work in practice.
It's a technical idea, but it basically involves having different levels of language models, each with different strengths and weaknesses.
Okay.
A smaller, faster model could be used for initial clue generation or document scoring, where speed is crucial.
Right.
Then a larger, more powerful model could handle things like evidence generation, and answer synthesis.
So like different levels of expertise within the AI system.
It's a good analogy.
Like the entry-level researchers gather the information and then the senior scientists analyze the data and make conclusions.
This approach could potentially address RetroLM's speed limitation.
Yeah, okay.
By using smaller models strategically, they could speed up the process without sacrificing accuracy.
Didn't they experiment with different size language models in the paper?
They tested RetroLM with a range of models from the smaller Llama 3.21b up to the larger Qwen 2.514b and Mistral 7b.
Did they find that the size of the model made a difference in performance?
They did,
Okay.
but maybe not in the way you might think.
How so?
The larger models generally performed better, but the smaller models still achieved good results, especially when used with the RetroLM approach.
So it's not just about raw computing power.
Right.
The way the AI uses that power is important as well.
This is what makes this research interesting. It's not just about building a bigger and faster AI.
Right.
It's about finding smarter and more efficient ways to process information.
I'm curious about the data sets they used. They had ones for both single-hop and multi-hop question answering.
Right.
Did RetroLM perform well on both?
They did see some differences in performance depending on the complexity of the task.
Okay.
On the single-hop datasets like natural questions and trivia QA, RetroLM did very well.
Because those tasks just require finding a single piece of information.
RetroLM's focused approach is very good for those types of questions.
Okay.
It can quickly find the information without getting lost in the details.
What about the multi-hop tasks where the answers might come from different sources?
Right.
Did RetroLM struggle with those?
On the multi-hop datasets like Hotpot QA and 2Wiki multi-hop QA, RetroLM was even better than the other methods.
So even when it had to do more work to find information from different sources, it still did well.
They did.
Why do you think it performed so well on those harder tasks?
The researchers believe this strong performance is because RetroLM can adjust the amount of evidence it gathers.
Okay.
For multi-hop questions, it can collect more evidence to create a complete answer while remaining efficient by being selective about what it retrieves.
So it knows when it needs to gather more information, but it's also smart enough to avoid being overloaded with too much information.
It finds a good balance between getting all the information it needs and efficiency.
Right.
Table 6 in the paper shows how well it performed on each data set.
Yeah.
And it's clear that RetroLM consistently outperforms the other methods no matter how complex the task is.
This approach is elegant. It seems like they've found a way to mimic how humans think and learn.
I agree. I think this research could change how we think about AI's role in information processing.
It's amazing to think about.
It is.
We're basically teaching machines to think like humans, and in doing so, we might discover something about how our own minds work.
That's an interesting idea, and it's something we might have to think more about as AI systems become more complex.
Right.
For now, I think RetroLM is a significant development in our journey to understand intelligence.
I agree. I'm curious to see what future research in this area will uncover.
Me too.
Before we finish up, I wanted to touch upon something else from the paper.
Okay.
They did an analysis of how the number of evidence pieces retrieved affected the model's performance. I thought that was interesting.
They were trying to see if there was a sweet spot,
Right?
an ideal number of pieces of evidence that would produce the best results.
Yeah.
What they found was very insightful.
What did they learn from this?
For the single hop tasks, they found that the model's performance improved as they increased the number of evidence pieces.
Okay.
Basically, the more evidence it had, the better it was at answering the question.
That makes sense. The more information you have, the easier it is to find what you're looking for.
However, for multi-hop tasks, there was a slightly different pattern. As they increased the number of evidence pieces, performance improved initially, but then it plateaued.
So having more information didn't necessarily lead to better answers.
This suggests that there's a balance between having enough information to create a complete answer
Right.
and avoiding too much information for these complex multi-hop tasks.
If the AI has too much information to process, it might get confused.
The researchers believe this plateau effect occurs because as they increase the number of evidence pieces, both helpful and distracting information is introduced.
It's like trying to solve a puzzle with too many pieces.
Right.
Some pieces might fit, but others just make it harder to see the bigger picture.
That's a good analogy.
Yeah.
It shows how important it is in AI research, not just to give the models more data, but to give them ways to intelligently process and filter that data, understanding what's relevant and ignoring what isn't.
RetroLM seems to be doing a good job of that.
We still have the case studies from the appendix to look at.
Okay.
These examples help make these ideas more concrete.
Tables 9 and 10 show RetroLM's output for single-hop and multi-hop question answering tasks.
Right.
Let's start with Table 9, the single-hop example.
Okay.
What do you see?
RetroLM clearly breaks down its thought process.
Okay.
You can see the clue generation and evidence generation stages.
It's like we can see inside the AI's mind and understand how it's thinking.
It's not just about seeing the results.
Right.
It's about understanding the steps the model took to get there.
Let's look closer at example #1 in Table 9 from the Natural Questions dataset.
Sure.
The question is, when does the movie The Star come out? What does RetroLM do?
As we've already discussed, the first thing it does is generate the clue, the star, which is a likely key phrase for finding information.
Right, and then it uses that clue to find evidence.
It presents the evidence sequentially, with each piece containing the clue, the star, and additional context to help answer the question.
In the final piece of evidence, it provides the answer.
Right.
The film was released by Columbia Pictures on November 17, 2017 in the United States.
This shows how RetroLM retrieves and presents information.
What about the other single-hop examples in Table 9?
Yeah.
Do they follow a similar pattern?
In each example, RetroLM generates a clue, retrieves evidence containing that clue, and then provides the answer.
So it seems like it has a good strategy for answering these single-hop questions.
What's remarkable is that this strategy is effective across different data sets and types of questions.
Okay, let's look at the multi-hop examples in Table 10.
Okay.
These are the questions where the AI needs to combine information from multiple sources.
Right.
Do you see any differences in RetroLM's approach?
The clues generated for these multi-hop questions tend to be more complex.
Okay.
This reflects how the AI needs to consider more information to get to the answer.
It's recognizing that these questions are more nuanced.
The evidence retrieved for multi-hop questions is also more extensive.
Right, because it needs to combine information from different sources.
Think of it like it's creating a story connecting the pieces of evidence together to make sense.
I'm looking at example #2 in the 2Wiki multi-hop QA dataset.
Okay.
The question is, where was the director of the film Ronnie Rocket born? It seems like RetroLM had to search quite a bit to answer that one.
The clue it generated was Ronnie Rocket, but it needed more information to determine the director's birthplace.
Looking at the evidence, we see that it pulls information about the film David Lynch, who was involved in the project.
Yeah.
And it finally finds information about Lynch being born in Missoula, Montana.
So it's slowly finding the answer from these different sources.
It's amazing how it can navigate this information and extract the details.
And it's able to do this while remaining efficient.
Yeah.
Compared to traditional RG systems, it uses far fewer tokens.
So it's not just smart, it's also resourceful.
Let's compare this with the naive constrained beam search method. Tables 11 and 12 show these two approaches.
Right.
The differences are pretty clear.
The naive approach, which relies on corpus-level constraints, has a lot of trouble with these questions.
It does.
It gets distracted by irrelevant information, which leads to incomplete or inaccurate answers.
This is a good reminder that having access to information doesn't mean you understand it.
Right.
You need a strategy to process and filter that information.
RetroLM combines clue generation, document scoring, and forward-looking evidence generation.
Right.
This is a much better way to retrieve and use knowledge.
In example, #1 from Table 11, the question is, who got the first Nobel Prize in Physics? RetroLM easily answers this.
Okay.
Generating the clues, Nobel Prize in Physics, and retrieving evidence that leads to the answer, Wilhelm Röntgen.
The output from the naive approach is completely different.
It is.
It's clearly not able to focus and find the right answer.
It shows that having a more focused and strategic approach like RetroLM is essential.
This has been a fascinating deep dive.
It had.
I feel like I have a much better understanding of how RetroLM works and why it's such a promising development in AI research.
It's been a pleasure discussing these concepts with you.
Likewise. For anyone listening who wants to learn more, I suggest reading the research paper.
It's a great resource.
It has a lot more detail and information.
Thanks for joining us.
Until next time.